Okay, today we're going to look at how to do lens questions, and the good news with lenses are that the formulas still work the exact same, and the concepts of drawing them and figuring out how to solve lens questions work exactly the same as mirrors, just with a few slight tweaks and tips that you need to remember. So keep in mind that a lens basically is just some sort of clear glass or plastic or something that has a higher index of refraction. So what that means is instead of it reflecting, so when we have a concave mirror, our light ray comes in and it reflects outwards at the same angle. With lenses, it works similar except it's refraction. So our light ray would come in and then it's going to refract through the lens. So instead of reflecting off a mirror, we're going to refract through a lens. But other than that, it works pretty much the same way. So the first thing you have to understand is what type of lens are we dealing with. So a converging lens then is a lens that bulges outwards on both sides. So it's a convex lens. So a double convex is the one that we typically draw and use. But you can see that we could have it just flat on one side, or it could even be slightly curved. As long as the inside's thicker than the outside, then we'd say it would be a convex lens. So convex lens converges. So if you remember, for a convex lens, a converging mirror was a concave mirror. So a concave mirror and a convex lens basically do the same thing. They both converge. And then the reverse is also true. If we have a diverging lens, which would be a concave lens, where the inside is thinner than the outside, that would do the exact same thing as a convex mirror. So diverging lens is concave, and a convex mirror, those two sort of work the same, and then our concave and convex lens works the same. So that's the first thing you need to remember, is sort of keep track that they work. And the way I usually remember is if I look at a back side, so let's suppose we have some sort of object and it's in front of a concave lens, what I do is I think of it as what is the back side of the lens. So the back side of the lens compared to the object is convex. So the back side of the lens works just like the same type of mirror. So when we're drawing these, in terms of drawing the diagrams, we basically do the exact same thing. And what we do is we only worry about the center of the lens. We don't have to worry about the actual rest of it. So we basically do the same thing. So if we have our object, so let's see if our object is there. Rule 1, for mirrors, we went through the focus and it bounced back parallel. So we go through the focus again, but now instead of bouncing back, it's going to refract through the lens, so it goes through the lens parallel. So through the focus and then through the lens parallel. And then rule 2 is the opposite. If we go parallel to the lens, it'll refract and go through the focus point. And then you can see where these two lines intersect. That is where our image is. And rule number 3, for mirrors, it was if it went through the center of the curvature of the mirror. So in this case, what we do is we go through the center of the mirror, or center of the lens. So if we go right through the very center of the lens, the line will just keep going straight because we won't get any kind of refraction. So you can see all three of those lines, all three of the rules line up to the same place and we get our image. So in this case, we would say because a lens, we want the light to go through and refract through, so we'd still call this a real image, even though it went through the lens, so that's different. Remember, with a mirror, if it's on the front side of the mirror, it's real. If it's on the back side, it's virtual, so that's opposite. Through the lens would be real, and we'd say it's still inverted, and in this case, it's larger. So now let's look at a diverging lens. So in this case, our object is out front again, so we're going to do the parallel rule first. So parallel, and it's going to diverge or spread out. So we extend that back with a dotted line through the focus, so those will line up. And then if we do the center rule, that's probably the next best one. So if we do it where it goes through the center, straight through, I'm a little bit off, but you get the idea, so that our image would end up being right about there. So with this diagram, there's the center one. You can see our little image shows up right there. So in this case, because it didn't go through the lens, we'd say it's a virtual image, and it's right side up or erect, and in this case it is smaller. Okay, so this is how typical glasses, most people that are nearsighted have glasses that are like this. So what it does is the image that's formed is a virtual image, right side up, but a little bit smaller. So when we're using formulas, we do the exact same thing. The only difference is we just have to be careful of the positive or the negatives again. So a converging lens, remember, is a convex lens. So we say our F is positive, and things that are on the other side, so our object was in front, our image was on the other side, we call that a positive. So you want to think of it as if it goes through the lens, it's positive. So a diverging lens was our concave one, and this is one where our object stayed on the front side, so we'd say it has a negative focus. So once again, if you think back to the back side, right, so the back side of this one would be a positive focus, the back side of this one would have our negative focus. And then the same thing, our image doesn't go through the lens, so we call it the virtual, which would be negative. So just that's about the only thing that's different than with mirrors. So let's do this question. So we have 1 over f equals 1 over do plus 1 over di. So they tell us it's a converging lens. So that's going to be good. So that means we have a positive f. So we have 1 over 0.22. And it says an object is 0.41 in front. So that'll be positive, 0.41. And that actually is asking what is the distance. It is going to be after it goes refracted through the lens. So we'd have 1 over di. So in our calculator, all we have to do is go 1 divided by 0.22 and minus 1 divided by 0.41. That gives us 2.1, and go 1 divided by that answer to get the reciprocal. And we get a di of 0.47. Because it's positive, remember it's going to be on the other side of the lens. So 0.47 meters would be our final answer. Characteristics, because it went through the lens, we'd say real. And we could figure out the height, and it would end up giving us a negative. So we could do that second part of the calculation if we want. It would be high ho over dido. And we could plug that in if we knew what the original height was, but we don't. But we know it's going to be a real image. It's likely going to be upside down and bigger or smaller depending on their distances. And that's it. So you can see pretty much the same thing as mirrors. You just got to remember a few differences. Think of the back side of the lens and think of it being upside down, right side up, and so on. And that's all.